Do you ever just look at a window? I mean, really look at it. It's solid, right? You can knock on it, but you can see straight through it. At the same time, a piece of wood or a sheet of metal, also solid, are like a brick wall to light. It's this everyday paradox that doesn't make a lot of sense until you realize the answer isn't about what we see. It's about something much, much smaller.
And this is where it gets really weird. We take sand, the stuff that's completely opaque. We melt it down, let it cool, and boom, it becomes perfectly clear glass. So how does that happen? How can tiny particles of light just blast right through a solid pane of glass, but get stopped dead by a block of wood? It feels like it shouldn't work that way. To get to the bottom of this, we've got to shrink ourselves down, way, way down. Because the answer isn't in our big visible world. The secret is hidden in the strange, fascinating, and kind of mind-bending rules of the quantum realm. Okay, so to figure this out, you really only need to understand the two main players in this little quantum showdown. On one side, you have the particles of light, the photons, trying to get through. And on the other, you have the electrons inside the material, acting like the world's toughest bouncers. So first up, we've got the photon. Just think of it as a tiny little bullet of light energy. Now, the photons that make up the light we can actually see, they're kind of wimpy. They only carry between about 1.65 and 3.1 electron volts of energy. Now, that number might not mean much right now, but trust me, it is the absolute key to this whole mystery. So just tuck it away for a minute.
And here's our bouncer, the electron. Now, electrons inside an atom are incredibly picky. They can't just absorb any old photon that comes knocking. The photon has to show up with the perfect amount of energy, like a key fitting a very specific lock, that allows the electron to leap up to a higher energy level. If the energy isn't an exact match, the electron isn't interested. The photon gets ignored completely.
So that's the rule for one single lonely atom. But what happens when you get trillions and trillions of atoms together to form a solid? Well, the whole rulebook gets a rewrite.
All right, let's walk through this. For an individual atom, you can imagine electrons living on specific rungs of an energy ladder. But when you pack all those atoms together into a solid, their ladders basically merge and blur together. What you get are these giant, continuous superhighways of allowed energy called bands. There's a lower band packed with electrons and a higher, empty band they could potentially jump to. And separating them is this huge, forbidden zone, a chasm called the band gap.
And this band gap, this is everything. It's the price of admission. It is the absolute minimum amount of energy a photon needs to give an electron so it can make that epic leap from its crowded home, the valence band, up to the wide open spaces of the conduction band. If the photon can't pay that energy toll, the jump is impossible.
So, this is the crucial part. That band gap, that energy chasm we've been talking about, it's actually the secret code. It's what determines, at a fundamental level, whether something lets light through or blocks it.
And you know what? The code is beautifully simple. It's just this. If an incoming photon has less energy than the material's band gap, the electrons literally can't absorb it. There's no energy level that can jump to. So the photon just sails right on through, untouched, and that's what we call transparent. But if the photon has energy that's equal to or greater than the band gap, an electron gobbles it up, makes the jump, and the light gets blocked. The material is opaque. Simple as that.
And this one rule explains pretty much everything. For metals, the bands actually overlap, so there's basically no band gap. Any photon, no matter how weak, can be absorbed and then immediately re-emitted, which is what we see as reflection. That's why metals are shiny. For semiconductors, the band gap is small, right in that 1 to 3 eV range, a perfect match for visible light, so they absorb it, making them opaque. But then you have insulators. Insulators have a huge band gap.
And you probably see where this is going. Glass is a textbook example of an insulator. It falls right into that category, which is our final clue.
So get this, the band gap for the silicon dioxide that makes up glass is about 9 electron volts. 9! Now remember the energy of visible light? Our most powerful little photon is barely scraping by with 3 eV. It just doesn't have a chance. Trying to cross that 9 electron volt gap is like trying to long jump across the Grand Canyon. It is just not going to happen.
And there it is. That's the big aha moment. The photons of visible light are just fundamentally too weak to interact with the electrons in glass. They can't pay the energy price to cross that enormous band gap. And so with nowhere to go and nothing to do, they just fly straight through. That is the quantum secret to why glass is see-through.
Okay, so
Now that we've cracked the code, we can use this new quantum superpower to finally understand why all those other things, sand, wood, and metal, are so stubbornly opaque.
So what about our original mystery, the sand? Sand is also silicon dioxide, which means it has that same gigantic 9 eV band gap. So why isn't it transparent? Well, the difference isn't quantum, it's physical. Sand is a jumble of zillions of tiny, imperfect crystals. At the edge of every single one of those grains, light gets bounced and scattered in a million different directions. But when we melt it, we erase all those boundaries and create one big, smooth, uniform material. We allow its natural, built-in transparency to finally shine through.
And those other materials? We already saw that metals, with their non-existent band gap, have a whole sea of electrons just ready to absorb and reflect any light that hits them. That's their shininess. Wood is a totally different story. It's made of complex organic molecules that have all sorts of smaller energy gaps, many of which are perfectly sized to absorb the photons of visible light. That absorption is what gives wood its color and, of course, makes it opaque.
But understanding this quantum secret is about more than just solving an old riddle about windows. It actually gives us a blueprint. It gives us the power to engineer transparency itself.
And this isn't some far-off sci-fi concept. We are doing this right now. By carefully designing materials with specific band gaps, a process called band gap engineering, we can create incredible things, like transparent ceramics, so-called transparent aluminum that are as clear as glass but unbelievably strong, or transparent conductors, the magical material that makes the touchscreen on your phone work. We are literally manipulating the quantum world to build the world around us.
So, the next time you look out a window, I want you to remember that incredible quantum dance that's happening. A whole army of light particles just a little too weak to pay the toll being allowed to simply pass through. It really makes you wonder, doesn't it? Now that we understand the fundamental code for transparency, what on earth will we choose to see through next?